Today, in this video, we will see numerical on rectangular bar subjected to triaxial loading. Numerical is a steel bar 35 mm by 35 mm in section and 100 mm length is acted upon by a load of 180 kN along its longitudinal axis and 400 kN and 300 kN along the axis of lateral surfaces. Determine change in the dimension of bar, change in volume, take modulus of elasticity capital E is equal to 205 gigapascal and Poisson's ratio is 0.3. So see in this figure, this is rectangular bar of height 100 mm. This is H, height 100 mm, breadth 35 mm. This is B and depth also 35 mm. Tata. Load of 180 kN along its longitudinal axis. P horizontal direction is x, vertically y axis and this z axis. So stress in load in x direction is 400 kN. Load in y direction is this 400 kN acts on this rectangular bar like compressive load. See this arrow, that's why negative 400 kN. And load on y direction is also acting as a compressive 180 kN load minus 180 kN. And this PZ also acts like compressive minus 300 kN. To find change in dimension of the bar. Dimension of bar, change in dimension of bar, that means change in height, change in width and change in depth. Next, change in volume. Capital E modulus of elasticity is 205 gigapascal. 205 into 10 raised to 3 megapascal. And Poisson's ratio is 0.3. Now solution. Step 1. Finding stresses in all direction. First find stress in x direction. Stress is denoted as sigma and x direction sigma x. Stress in x direction is load acting on x direction divided by cross-sectional area. So load acting on x direction is this minus 400 kilonewton and cross-sectional area is height into depth. Px is minus 400 kilonewton, and for conversion of this minus 400 kilonewton into Newton, multiply it by 10 raised to 3. Minus 400 into 10 raised to 3 Newton is load acting on x direction divided by h into d. H is 100 multiply by d is 35. Depth. Minus 400 into 10 raised to 3 divided by 100 into 35. Minus 114.29. Unit of stress is MPa, megapascal. Next, find stress in y direction. Stress in y direction denoted by sigma y is equal to load in y direction to the cross-sectional area. Load in y direction is minus 180 kilonewton and cross-sectional area is B into D, width into depth. B is 35 multiplied by D is also 35. Minus 180 into 10 raised to 3 divided by 35 into 35. Minus 146.94. MPa. Next, stress in z direction. Stress in z direction is sigma z, load in z direction to the cross-sectional area, this capital H into small b. That means this PZ load acting on this capital H into small b area, cross-sectional area. PZ load acting on capital H into small b cross-sectional area, and PZ is minus 300 kilonewton minus 300 into 10 raised to 3 Newton, and H is 100 multiplied by 35. Minus 300 multiplied by 10 raised to 3 divided by 100 into 35. Minus 85.71 MPa. Stress in x direction is minus 114.29 MPa. Stress in y direction is minus 146.94 MPa. Stress in z direction is minus 85.71 MPa. Load acting on z direction is 300 kilonewton, and stress acting on z direction is minus 85.71 MPa. load acting on y direction 180 kilonewton and stress acting on y direction minus 146.94 MPa. Load acting on x direction 400 kilonewton and stress acting on x direction minus 114.29 MPa. That means see this less cross-sectional area, small b into small d, stress comes bigger. When cross-sectional area is small, then stress comes bigger. And when cross-sectional area is big, stress comes smaller. That means stress is inversely proportional to cross-sectional area. Now, next, find strain. Step 2. Strain for rectangular bar subjected to triaxial loading. First find strain in x direction. Strain in x direction formula we seen in derivation. Strain in x direction is equal to 1 upon Young's modulus multiplied by stress in x direction minus Poisson's ratio into stress in y direction plus stress in z direction. X is equal to modulus of elasticity is 205 into 10 raised to 3 MPa. 1 upon 205 into 10 raised to 3 MPa. Stress in x direction is minus 114.29. Poisson's ratio is 0.3. Stress in y direction minus 146.94. And stress in z direction minus 85.71. Minus 146.94 minus 85.71 multiplied by 0.3 minus 114.29 minus answer divided by 205 into 10 raised to 3 minus 2.17 into 10 raised to minus 4 is strain in x direction. Now next calculate strain in y direction. Strain in y direction Ey is equal to 1 upon Young's modulus multiplied by stress in y direction minus mu in bracket stress in x direction plus stress in z direction. 1 upon calculate this minus 114.2 minus 114.29 minus 85.71 multiplied by 0.3 minus 60. That means minus 146.94 plus 60 divided by 205 into 10 raised to 3 minus 4.24 into 10 raised to minus 4 each strain in y direction. Now next calculate strain in z direction. Strain in z direction denoted by Ez is equal to 1 upon Young's modulus multiplied by stress in z direction minus Poisson's ratio in bracket stress in x direction plus stress in y direction. 1 upon Young's modulus is 205 into 10 raised to 3. Stress in z direction is minus 85.71 minus Poisson's ratio 0.3. Stress in x direction minus 114.29 and stress in y direction minus 146.94. Minus 114.29 minus 146.94 multiplied by 0.3 minus 78.369 divided by 205 to 10 raised to 3. So strain in z direction is minus 3.58 into 10 raised to minus 5. Step 3. Calculate volumetric strain for rectangular bar subjected to triaxial loading. EV is equal to EX plus EY plus EZ. EV is equal to minus 2.17 into 10 raised to minus 4 plus minus 4.24 into 10 raised to minus 4 plus minus 3.58 into 10 raised to minus 5 minus 2.17 into 10 raised to minus 4 plus minus 4.24 into 10 raised to minus 4 plus minus 3.58 into 10 raised to minus 5. Minus 6.77 into 10 raised to minus 4. And our objective is calculation of change in dimension of the bar. Step 4, change in dimension of bar. First calculate this B. For calculation of this B, strain in x direction. Ex is equal to change in width to the original width, because this B is along the x-axis and strain in x direction is change in length to the original length. That means this change in width to the original width. Change in width is equal to strain in x direction multiplied by width. Strain in x direction is minus 2.17 into 10 raised to minus 4. And B is 35 mm. Minus 2.17 into 10 raised to minus 4 multiplied by 35 minus 7.595 into 10 raised to minus 3. That means 0.0076. 4.6 into 10 raised to minus 3. This is minus mm. This is change in width. Next, calculate. Change in height. For calculation of change in height, use formula strain in y direction, because this height is along the y direction. Ey is equal to change in height to the original height. Strain in y direction is equal to change in height to the original height. Change in height is equal to Ey into capital H. Ey is minus 4.24 into 10 raised to minus 4. And height is 100 mm. Minus 4.24 into 10 raised to minus 4 multiplied by 100. 0.0424 m. This is change in height. Next, third, calculate change in depth. This d change in depth is along the z axis and strain in z axis is equal to change in depth to the original depth. Ez is equal to change in depth to the original depth. Change in depth is equal to Ez into small d. Ez is minus 3.58 into 10 raised to minus 5. Multiply by this d is 35. Change in depth is equal to minus 3.58 into 10 raised to minus 5 multiplied by 35 minus 1.253 into 10 raised to minus 3. That means this change in depth is minus 0.0013 mm. Next, calculate change in volume. For calculation of change in volume, we need EV is equal to change in volume to the original volume, and EV is EX plus EY plus EZ. This EV is minus 6.77 into 10 raised to minus 4. Therefore, change in volume is equal to EV into V minus 6.77 into 10 raised to minus 4 multiplied by total volume of that steel rectangular bar 100 multiplied by 35 multiplied by 35. Height multiplied by width multiplied by depth. Change in volume minus 6.77 multiplied by 10 raised to minus 2 multiplied by 100 multiplied by 35 multiplied by 35 minus 82.93 is change in volume in mm cube. Minus 82.93 mm cube is change in volume for that rectangular bar subjected to triaxial loading. Thank you very much.